Welcome. My name is Harnit Saini and I am Assistant Professor in AKGEC Engineering College. Today the topic of our discussion is deadlock. A set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. Right? There can be a situation in a system when there are a number of processes and each process is waiting for the resource. Then only it will be completed. And that resource is acquired by some other process who is already waiting for some other process. So this way, there is a circular wait for one process is waiting for the other process to release the resource. It is further waiting for the other process to release the resource. This way, there is a cyclic process, and this type of situation, none of the process is going to complete because everyone is in waiting only, right? So such type of situation is called a deadlock. For example, the system has two tape drives, right? P1 and P2 each hold one tape drive and each needs another one, right? Now there are two processes, P1 and P2, and we have two tape drives, right? One tape drive is with P1 and one is P2. P1 is waiting for P1 to release this tape drive and P2 is waiting for this P1 to release the first tape drive. Now both of are holding the resources plus they are waiting for the other to release. So this way we can see that there is a circular or cyclic wait, and this type of situation is called a deadlock, right? Then if we consider a semaphore, right? The semaphores A and B, we have P0 is waiting, has put a wait on A and wait on B, and P1 is put it wait for B and then wait for A. Such a situation is also a type of deadlock problem. Now see, if we take a lifetime example for a deadlock, there is a narrow bridge and these are the broad roads, right? And some vehicles are coming from this side and some vehicles are coming from this side, right? And the traffic can move only in one direction. Each section of the bridge can be viewed as a resource. Now we will compare the bridge to a resource. This resource is a bridge and these all vehicles are the processes. Now all these processes require this particular resource, right? If a deadlock occurs, it can be resolved if one car backs up. Now, this car cannot move forward because this car is blocking the way. Similarly, for this car is blocking the way. This car also doesn't move, right? Now they are waiting for each other. With someone or clear the way, we can move forward. And if this car wants to go there, it cannot go because this has stuck the way. Similarly, this car cannot go, this has stuck the way, right? Now, all these processes one by one are getting into the waiting state. So this says that if this situation can be overcome if one of the driver moves the car back. When he will move the car back, this will move on and then this will again move on and the system will go on, right? Several cars may have to be backed up if a deadlock occurs. Now there can be a situation, we have taken that these are the two cars only, but there can be a situation when number of cars like this, here also they are queuing up, right? So if we want that, and here also they are queuing up, right? Now if we want to move, to make the system to work, we have to roll back all the cars of one side, either of this or this, right? So this way, more than one process can also be rolled back to make the system work, right? So it cannot be that only one process if we are rolling back and our system is in running situation, right? It can be there and the situation where we have to roll back more than one process. Then here, starvation is the major problem. Maybe there is a situation which the process that we are choosing to roll back is always the same process again and again. We are choosing that process only because it has a lower priority or maybe it is not that important process, right? So in this way, there is a starvation for that particular process. So it is going into wait only every time, right? So we have different procedures, like we have aging factor, which can which is the solution to the starvation problem. Now see the system model. Suppose there are resource types R1 to Rn, right? CPU cycles, memory space, and input-output devices are the associated with all these resources. Each resource have Ri has W1 instances, right? We have each resource not of one type but of number of types, which is W1. Each process utilizes the resource as follows. First, it will request the resource, then it will use that resource, and then after that, after using it, it will release the resource. Now, the four important conditions for a deadlock to occur are mutual exclusion, hold and wait, no preemption, and circular wait, right? In mutual exclusion, the rule says that only one process will take the resource at a time, right? If a process is needed one resource, only that process will use that resource. No, that resource will not be shared with other processes, right? Then hold and wait. Hold and wait says that you are holding some resources, means the process is holding some resources and they are waiting for some other resources, means they are blocking the holding resources also, because they are not using them but they are just holding it, and other processes are also not able to use them because they are holding it and waiting for other resources. A process holding at least one resource is waiting to acquire additional resources held by other processes. This type of thing is done by many processes in the situation, right? Then no preemption. No preemption means a resource can be released only voluntarily by the process holding it after that process has completed its task, right? No preemption means in between this is the process of completion, start to completion, the process will not release the resource, right? It will release the resource only when it has completed all its execution. Circular wait. As we discussed earlier, there exists a set P0, P1 up to P10, suppose, of waiting the processes such that P0 is waiting for the resource. This is P0 only. I will tell you what the meaning is. P0 is waiting for P1, P1 is waiting for P2, P2 is waiting for P3, P3 and so on, and the last process is waiting for P0, right? You can consider it like this. P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, P4 and so on, Pn, and the last process is waiting for P1, right? So this way there is a circular wait and none of the process is able to complete. Now, methods of handling the deadlock. First is ensure that the system will never enter a deadlock state. Means you have to use those mechanisms so that we can make it sure that there is no deadlock in future. Means you take the prior information, check whether if the requests are being given, whether the system will go or it will halt due to a deadlock. Then allow the system to enter a deadlock and then recover. This is deadlock detection and recovery, where we assume that there will be no deadlock, and if the deadlock occurs, we will recover from it, right? Ignore the problem and pretend the deadlocks never occur in the system, used by the most of the operating systems, including Unix. Here, what we say, we assume that there will be no deadlock in future, and by chance, if deadlock occurs, we restart the system again, right? This is the simplest way to be done. Now, how to prevent a deadlock? Deadlock prevention. So, first condition of the deadlock was mutual exclusion, where we said that the resource will not be in the shareable mode. Only one process, if it is holding that resource, it will use that resource, no other will be using it, right? Not required for shareable resources, because mutual exclusion, if the system resource can be shared, then don't put the mutual exclusion rule on that particular resource. This says that. And must hold non-shareable resources. Only mutual exclusion is implemented on the resource which is in not shareable mode, right? For shareable, we don't need to put mutual exclusion rule. Then hold and wait. In hold and wait, the rule was this process is holding the resource and it is waiting for some other resource which is holded by some other. So if we want to prevent the deadlock, we have to make this condition false. How? You must guarantee that whenever a process requests a resource, it does not hold any other resource, right? If I'm holding resource A, now I require resource B. So before acquiring resource B, I have to release resource A. This way we can make this condition false, and we can prevent the situation of a deadlock, right? Require processes to request be allocated all its resources before it begins execution, or allow the process to request resources only when the process has none. Now, how to implement hold and wait? There are two ways, right? First, ask the process how many resources you want. You give all the resources to it at one time and let it complete, right? But this can be a situation when that process reads the request later at the end of the program. So in the meantime, that resource can be used by some other process, right? So there is the other process may be waiting and the first process is not using that particular resource. So the other way out is that if you are requesting a resource, then leave the first resource and then ask for the next resource. Then in this situation, we can have that I have done my work with the resource 1, you can take it, I will use resource 2. And whenever I will require resource 1 again, I will again acquire it, right? This is the theory for this. But here what happens, there is low resource utilization and starvation can be possible, right? Now, the third condition was no preemption. In that, we told that if a process has acquired a resource, it will not release the resource until it is completed. Means we will not stop a process in between, right? If a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all the resources currently being held are released. Now, suppose I am having 5 resources. I'm doing my execution. I'm working with it. Okay. Now I require the 6th process. Now the 6th resource. Sorry. Then I am not able to get that resource due to because it is acquired by some other process. Now what will I do? I will release all the 5 resources which I am holding. Right. So that I have to wait now for the 6th resource. Why to hold the 5 resources? Why to block all the 5 resources which can be used by some other process, right? Preempt resources are added to the list of the resources for which the processes are waiting. So we have in a way taken the resources from the process, and we can declare that these resources are free and they can be acquired by some other processes, those who are waiting for these resources. Processes will be restarted only when it can regain its old resources as well as the new ones that it is requesting, right? Now what will happen if the process want to restart now? Suppose he is getting all the resources which he is demanding. He has to acquire all the old resources also. Okay, all the resources when he will get it at one time, then only it will run and go to completion, right? Circular wait. Circular wait means impose a total ordering of all the resource types and require that each process request in the increasing order of the enumeration, right? Now in circular wait, we discussed that P1, suppose P0 is requesting a resource that is holded by P1. P1 is requesting a resource holded by P2, P3, and this is again P0. Now to make this condition false, what we will do, we will assign one number to every process, right? Now, if each process requests in the increasing order of the enumeration, right? P1 can acquire resource only when the number which has the higher, which means P0 will get the resource first, then P1 and P2 and P3 if they are all in the same weight, right? Then if we will satisfy the request in the increasing order of the enumeration, right? Require that each process requests resources in an increasing order of the enumeration, right? Deadlock avoidance now. First we did deadlock prevention, means out of 4 conditions, mutual exclusion, no preemption, hold and wait, and circular wait. These 4 conditions were there for a deadlock, right? Now for deadlock prevention, we will make one of these conditions false and we can prevent a deadlock. Now for deadlock avoidance, requires the system some additional priori information available, right? Simplest and most useful model requires that each process declares maximum number of resources of each type that it may need. Now, when the process enters into the system, it has to declare that in my lifetime, how many resources I will use. So that OS come to know that these resources will be acquired by this particular process. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Because in avoidance, what we'll do, we will virtually assign the resources which are demanded by the processes, and we will check with the algorithm if we are giving these requests whether there will be a cycle or not, or there is a circular wait or not. And if we find there is a circular wait, then we will not okay the request. We will not satisfy the request. We will wait. We will tell that you have to wait at that situation. Every time a process wants to acquire a resource, we will execute a deadlock avoidance algorithm, which we will discuss further, to check that if in future if we satisfy this request, then it will be a deadlock or not. And if we found that it is okay, no deadlock, no circular wait, we can okay the request. Now, resource allocation state is defined by the number of available and allocated resources and maximum demands of the process. Okay. Now the process have to declare, OS has to make the record that what is the maximum need, maximum demand of that particular process. At that particular moment, how many resources are allocated to that process and how many resources are available with us, right? How will we calculate available? We will maximum minus allocated resources and we will get the available resources, right? Now, what is a safe state? When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state, right? Now we have to see that what request is there, right? We will check the algorithm whether there will be a deadlock or circular wait or not, right? If we find that all the situation is fine and we can allocate that request, that is called a safe state. System is in the safe state if there exists a safe sequence of all the processes. For all the processes, we will do the same. And we got the safe sequence then. We got a sequence in which we can give the resources. We allocate the resources. Now, when according to our algorithm, what sequence we got, we will allocate the resources in that sequence only. Right? Sequence P1 to Pn is safe if for each P, means for each process, the resources that Pi can still request can be satisfied by currently available resources, plus the resources held by Pj with j is less than equal to 1, right? Suppose there is a smaller number process has released the resources. We will add those resources into the available resources. Then for the next process, we will check what are its requests, means what are the requests which he can make in future. We'll compare it to the available resources. If we can satisfy it, we can allocate. We can feel that this system will be, this process will be allocated resources, right? If PI resource needs are not immediately available, then PI can wait until PJ have finished, right? Now PI will wait if the available resources are lesser than its demand, right? It will wait. We will check the other next process then, right? PJ is finished, PI can obtain needed resources, execute, return allocated resources, and terminate. Now what we'll do? The other process, it was waiting. The other process we checked, it was okay. We gave the resources, and it will return all the holding resources also. Then number of resources, available resources will increase, and we can satisfy the demand of PI, which earlier we made it waiting, right? When PI terminates, PI plus 1 can obtain its needed resources, and so on. Basic facts you should know. If a system is in the safe state, then there will be never a deadlock, right? If it is in the unsafe state, then there is a possibility of deadlock. Means it may or may not enter a deadlock situation. And in avoidance, ensure that the system will never enter in an unsafe state. In avoidance, we have, prior to allocation of resources, we have to make sure that system does not enter a deadlock. Now, Banker's algorithm is the algorithm which we can use to check the deadlock in future. So it is where the situation where the Banker's algorithm is used is where we have multiple instances of resources. Each process must priorly claim maximum use. When a process requests a resource, it may have to wait. Maybe it have to wait, right? When a process gets all its resources, it must return them an infinite amount of time, right? When it is completed, then it will return the used, which were resources it was holding earlier, and now what resources it used, it will return all the resources, right? Now the data structures for the Banker's algorithm. First, you should know the matrices which are used in this, right? First one is the available, right? Vector of variable of length m. If j is equal to k, if available j is equal to k, there are k instances of resources rj are available, right? If we have this situation, j square bracket is equal to k, means that k instances of resource j are available, right? In this, right? Maximum is a matrix. Max ij is equal to k, means that the process pi may request at most k instances of resource j, right? Pi, first number, pi is first, the number is for the process and the second one is for the resource. Process pi can have maximum resources of pk, j amount of resources of pk. Allocation ij means process pi is allocated with j instances of process, k instances of process resource j. Listen again. Process pi is allocated k instances of resource rj, right? Pi is currently allocated k instances of resource rj. What is the need matrix now? Need matrix, need ijk is means process pi needs k instances of resource rj, right? The pi may need k more instances of rj to complete its tasks. Now need, how to calculate need? Maximum minus allocation. Maximum is the demand of which the process declare while entering, that I will maximum take these number of resources, right? Allocation means at that particular time how many resources are allocated. When we will subtract this, we will get the need. Means in future, these number of resources can be required. Now first we will run the safety algorithm, right? Let work and finish be the vectors of length m and n respectively. Work is equal to available. Means in work we have put the available resources. Available resources are those resources which are not allocated to anyone and they are free, right? Finish, we will set for every process finish is false because no process is finished in the starting, right? Now we will find I such that finish I is false. We will find that process which is finished, right? And then need is less than equal to work, means its need is less than or equal to available. Because work is what? Available. Means we should have available resources more than what it is, more or equal to what it is requiring. If no such I exists, assume that when we are checking all the resources, we will not get false at once, all the on true, and then after that we will search the need of that, right? Then what we'll do, we will go on searching like this, right? We will, if we doesn't get any I, we will go to 4, right? Go to step 4. Then this means finish I is equal to true and all the system is in the safe state. But if we doesn't get any false, any true process, we finish true, then what we'll do, we will see that if the need is less than work, if it is okay, then we will work is equal to work plus allocation, means we can complete that process and we will add the allocated resources to the available resources, and it will means the number of free resources will increase, and we will try to finish one process, will true, and we will go to step 2. When one process finishes, we go to step 2 till all the processes are finished, right? After the second part of Banker's algorithms, resource request algorithm, right? Now we have seen that there are processes how they will be allocated resources to them. When request is less than equal to need, then go to step 2, right? Request is less than need, then request is available. It should be less than available also, right? Need, it should be less than need also, it should be less than the free resources also. Then if it is okay, then we will go to step 3, otherwise we will make it wait. When these both conditions are true, then what we will do, we will allocate that particular request and we will minus it from need. Now need will be less because one of the requests which the process made is fulfilled, right? It is safe if resources are allocated to PI. It is unsafe if PI must wait and older resource allocation state is restored. If the particular process has to wait for the timing, it is unsafe state. Maybe it can end to a deadlock. But if it is request is allocated, then means it is a safe state for that particular process. Now let's take an example. There are 5 processes P0 to P1, and see here, these are resources A, B, C. Available are 3 instances of A, 3 instances of B, and 2 instances of C. These are available, means they are free, they are not allocated to everyone. These are the allocated ones. One resource, one instance of B is allocated to P0. Similarly, 2 instances of A are allocated to P1, right? This way, these numbers are written. Now, max means total in future, A will request 7 instances of A, 5 instances of B, and 3 instances of C, right? So, in P0, this is for P0. P1 will take 3 instances of A, 2 instances of B, and 2 instances of C. Similarly for other processes. Now we will take out the need matrix. Need matrix is maximum minus allocation. maximum minus allocation will be the need, right? See, maximum minus allocation is the need, right? See how we are subtracting. See, 7 minus 0 is 7, 5 minus 1 is 4, 3 minus 0 is 0. So 740 for P0 is the need, right? See, 743 is the need. Oh, sorry, 3. 3 minus 0 is 3, right? Now this way we will calculate need for all the processes. Now this need is compared to the available. 332, right? Now see, 332 is the available. First is P0, we cannot satisfy because A requires 7 instances, we have only 3 instances, so it will not be satisfied. P1 can be satisfied, right? Because it is requiring 1, 2, 2. This is less than 3, 2, 2, right? So what will P1 will go? P1 is the safe sequence, it will return all these resources. And what are the number of resources now? 1, 5 and 4. We will add these resources to this. Now P2 will, this is over now, okay? P2 will not go because it is requiring 6 instances away which are not available. P3 will go, right? It will run and it will add these resources. So how much we will get? 3, 6 and 5. 4, 6 and 5, right? This will be done. Then P4 can be allocated 4, 3, 1, 4. It is less, so it will also be added to it, right? It is also complete now. Now the resources are 8, 3 plus 6 is 9, 5 plus 1 is 6, right? Now we come back to P0, or we come, because 2 is more, ID is more, we will check first 2. 2 will be completed, 600, and we have 896, so it will be completed. So these are will be added to this 14, 9 and 6. Now the demand of P0 will also be completed, right? So this is not a deadlock. Deadlock detection, we will allow the system to enter into deadlock state, and then we will invoke some detection algorithm. We will tell that some deadlock has occurred, and we have number of recovery schemes, right? So when first method is to abort all the deadlock processes and restart it. Other method is abort one process at a time until the deadlock cycle is eliminated. Now, how to abort this? We have to choose one criteria to choose the victim who will be aborted. Maybe it is priority, right? How long the process is computed, resources the processes has used, its needs, how many processes will need to be terminated, or it is interactive or batch. These can be the criteria to choose the victims, right? Select a victim which minimizes your cost, right? Then roll back it and restart the process, right? It may lead to the problem of starvation, which we will solve with the number of with the aging term. Thank you very much.